These are the answers to the AP Chemistry packet on topics 8.4 and 8.5. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now let's take a look at our first multiple choice question. Question 1 says the following. A student combined 300.0 milliliters of 0.050 molar HNO3, that's called nitric acid, with 500.0 milliliters of 0.032 molar KOH, that's potassium hydroxide, and mixed the final solution thoroughly. The pH of the resulting solution should be closest to, and then we see 4 numerical choices. Now, this video does cover topics 8.4 and 8.5, but part of the foundation to get this question correct is to understand what type of acid is HNO3 and what type of base is KOH. That's actually falling under topic 8.2, pH and pOH of strong acids and bases. So you can see in that first essential knowledge statement that there are 6 strong acids that students should memorize for the AP Chemistry exam, and on that list is nitric acid, HNO3. Of course, potassium happens to be located in group 1 on the periodic table, so potassium hydroxide is an example of a strong base. It's a group 1 hydroxide. And of course, if we were just calculating the pH of the nitric acid, or if we were just calculating the pH of the potassium hydroxide, that would fall under topic 8.2. Now, take a look at one of the essential knowledge statements from topic 8.4, acid-base reactions and buffers. So when a strong acid and a strong base are mixed, they react quantitatively in a reaction represented by the following equation. So H plus from the strong acid combines with OH minus from the strong base to produce water. And then that last statement is very relevant to this particular question. It says the pH of the resulting solution may be determined from the concentration of excess reagent. So now back to question 1. If there is an excess of either the nitric acid or the potassium hydroxide, then that will cause the pH to be something other than 7. So at this point, we can't eliminate any of the choices until we know, is there an equal amount of moles of H plus and OH minus, or is there an excess amount of acid or an excess amount of base? So to start off this calculation, let's take volume times molarity to calculate the number of moles of each of these substances. So the first beaker contains 300.0 milliliters of this solution of 0.050 molar nitric acid. So first, I'm going to convert from milliliters to liters. So there's 1,000 milliliters in 1 liter. And then I'm going to use the molarity as a conversion factor. So 0.050 moles of nitric acid for every 1 liter. And if I do this math, 300 divided by 1,000 times 0.050, then I get the number of moles of nitric acid. And this happens to be a strong acid, so that number, 0.015 moles of nitric acid, is also the number of moles of H plus or hydronium ions in solution. So I'm going to label that first beaker as 0.015 moles of H plus. Now we're going to do a similar calculation for the second beaker, which is the solution of potassium hydroxide. So the volume of that solution in the second beaker is 500.0 milliliters. First, I'm going to convert from milliliters to liters, so divide by 1,000, and then using the molarity, there's 0.032 moles of potassium hydroxide for every 1 liter. And when I do this math, 500 divided by 1,000 times 0.032, this will give me the number of moles of potassium hydroxide. But this is a strong base, There's a 1-to-1 ratio between the moles of KOH and the moles of hydroxide in that formula. So that number, 0.016 moles, is also the number of moles of the hydroxide ion. Well, now, as you look at these two number of moles side by side, you can see that the number of moles of the hydroxide ion, 0.016, is slightly larger than the number of moles of the H plus ion, 0.015. So after this chemical reaction takes place between the strong acid and the strong base, there's going to be a little bit of leftover hydroxide at the end of this experiment. So the number of moles of hydroxide ions is slightly more than the number of moles of H plus ions. So at the end of this experiment, the pH of the combined solution should be greater than 7. So let's go ahead and eliminate choice A, which says the pH is 2.90. And let's eliminate choice B, which says the pH is 7. We know the pH has to be greater than 7 because of the excess amount of the hydroxide ions. Now let's calculate the number of moles of excess or leftover hydroxide in the combined solution. So 0.016 minus 0.015, and then that number represents the number of moles of the hydroxide ion that is left over or excess at the end of the experiment. Now be careful that you don't rush the process of doing calculations, because at this point, some of you might be thinking, I want to calculate the pOH of the solution, and you might be tempted to take the negative log of 0.001. But if you look at the units, this unit that we have right now is moles, not molarity, not moles per liter. So don't forget that when you take the negative log of either the H plus or the OH minus to calculate the pH or the pOH, that would be the negative log of the concentration of those ions. Not the number of moles, but the concentration. And if you notice, we have a total volume of 800 milliliters of the combined solution. Let's turn that number into liters. That would be 0.8 liters when you divide by 1,000. So the concentration of the hydroxide ion in that beaker at the end of the experiment is 0.001 mole of hydroxide dissolved in a total volume of 0.8 liters. Now when you do that math to get the concentration, 0.001 divided by 0.8, that is the concentration of the hydroxide ion. So when I did that math, I got 1.25 times 10 to the negative 3 moles per liter. Now we are only 2 steps away from determining the pH of the resulting solution. So we're 2 steps away. First, we're going to take the negative log of the concentration of the hydroxide. So you can see here on the equation sheet, there's the equation for determining the pOH. And then 14 is equal to the sum of pH plus pOH. If we do 14 minus pOH, we will get the answer to question 1. So the negative log of 1.25 times 10 to the negative 3, that will give us the pOH, and that works out to be 2.90. Now, if you look carefully at choice A, which we've already eliminated, 2.90 was the choice A answer. So some students might have gotten this far in their calculations and then forgot that what they were considering was pOH and not pH. So they might have chosen A if they weren't paying attention closely. So all we have to do now to go from pOH to pH is 14 minus 2.90. So the correct answer to question 1 is choice D. The pH of the resulting solution should be closest to 11.10. Now let's take a look at question 2. Question 2 says the following. What are the relative strengths of the acids and bases in the reaction represented by the equation above? So if we look at the details of this acid-base reaction, on the left side of the equation, I see OCl-, that is the hypochlorite ion, and it's reacting with HF, that's hydrofluoric acid. And then the two products of this reaction are HOCl, that's hypochlorous acid, and then F-, the fluoride ion. So there is a column devoted to acid strength where we have to compare hydrofluoric acid, HF, and hypochlorous acid, HOCl. And then there's also a column devoted to base strength. We're comparing the fluoride ion, F-, with the hypochlorite ion, OCl-. Now, at first glance, you might say, I'm not sure we have enough information to compare which acid is stronger, which base is stronger. But the key to unlocking this question is that equilibrium constant. So it's listed there on the right side of the equation. It says that the equilibrium constant, K, is equal to a number that is greater than 1. So the fact that the equilibrium constant K is greater than 1 is very important because it tells us which substances in this acid-base reaction would be favored at equilibrium. Now on this next slide, I'm going to show you a topic from Unit 7, which is equilibrium. This is topic 7.5. And in this essential knowledge statement, it talks about the fact that some equilibrium reactions have very large K values in which the products are favored at equilibrium, and then other equilibrium reactions have very small K values where the reactants are favored at equilibrium. And the fact that this K value, this equilibrium constant, is greater than 1, then this tells us that the products are favored at equilibrium. So now what I'm going to do is identify each one of these 4 substances as either an acid or a base. So starting on the left, we have OCl-, or the hypochlorite ion, and that behaves as a base, as a proton acceptor, and it reacts with HF, or hydrofluoric acid, which behaves as an acid, a proton donor. Now on the other side of the equation, there's also one acid and one base. So we have the hypochlorous acid, HOCl, that would behave as a proton donor if this reaction proceeds from right to left. And then we have F-, the fluoride ion, which if this reaction were to proceed from right to left, that would behave as a base, a proton acceptor. And the fact that the products are favored at equilibrium, because K is greater than 1, then this tells us that the OCl- ion is more likely to behave as a proton acceptor, producing the products that are favored on the right side of the equation. Similarly, the HF, hydrofluoric acid, is more likely to donate H+, again, to produce the products which are favored at equilibrium. So based on this information, OCl- is the stronger base, and HF is the stronger acid. So that's why the products are favored at equilibrium. Now, if you're wondering, what would have happened if the value of K would have been less than 1 instead of greater than 1? Well, everything would have been reversed. So if K were less than 1, then the chemicals on the right side of this equation would have been the stronger acid and the stronger base. But what we can see here is that because the products are favored at equilibrium, K is greater than 1, we have now identified OCl- and HF as the stronger base and the stronger acid. Let's go back and review those 4 choices in question 2. So now that we know that the OCl- or the hypochlorite ion is the stronger base, then the correct answer to question 2 is either choice A or choice C. And as far as acid strength, now that we know that HF, or hydrofluoric acid, is the stronger acid, then the correct answer is either choice D or choice C. So clearly, choice C is the correct answer to question 2. It identifies HF as the stronger acid and OCl- as the stronger base. And we know this since the value of K is greater than 1, it told us that the products are favored at equilibrium, which means that the reactants are the stronger base and the stronger acid. Now let's take a look at question 3. Question 3 says the following. A solution of 0.10 molar HNO2, that's nitrous acid, it has a pKa value of 3.40. This acid is titrated with 0.20 molar sodium hydroxide, NaOH. And the question asks, which of the following identifies the pH at the equivalence point of the titration and provides the correct justification? So as you examine these four answer choices in question 3, you can see that 2 of them indicate that the pH is equal to 7 at the equivalence point, and then 2 of them indicate that the pH is greater than 7 at the equivalence point. So a good strategy to get started in analyzing this question is to determine what type of acid do we have, strong or weak, and then what type of base do we have, strong or weak. So back to topic 8.2, pH and pOH of strong acids and bases. As you examine that list of the 6 strong acids that you should memorize for the AP Chemistry exam, you'll notice that HNO2 is not on that list. So HNO2, or nitrous acid, is classified as a weak acid. Now, if sodium hydroxide is a strong base, it's an example of a group 1 hydroxide. So we have HNO2 classified as a weak acid, and what I did is to calculate the Ka value. So we were given the pKa, which is the negative log of the Ka. I just did the opposite of that, so I did 10 to the minus 3.40, and I got a value for Ka of 4 times 10 to the negative 4. That's further indication that nitrous acid is classified as a weak acid. And as we understand that sodium hydroxide is a group 1 hydroxide, it's a strong base. Now, take a look at one of the essential knowledge statements from topic 8.4, acid-base reactions and buffers. So in this example of a weak acid and a strong base, when a weak acid and a strong base are mixed together and you get to the equivalence point of the titration, that is, if they are equimolar, that's what happens at the equivalence point, then the pH can be determined from the equilibrium represented by the following equation. At the beginning of the titration, you have HA, and it's reacting with hydroxide, but at the equivalence point, it's the A minus, the formula for the conjugate base, that will react with water to produce not only its conjugate acid, HA, but also the hydroxide ion. Now, specifically, the formula of our weak acid in question 3 is nitrous acid, HNO2. So what's the formula of the conjugate base? That would be NO2 minus, which is known as the nitrite ion. So NO2 minus is acting like a weak base. And on the next slide, I'll show you a graphic from my video for topics 8.4 and 8.5. So what you're looking at is a titration curve from a weak acid, strong base titration experiment. And what you can see highlighted in yellow is a comment about the pH for this particular titration experiment from that video is greater than 7. And I say that we have to consider the presence of the conjugate base, A minus, which reacts with water as follows. So that same equation you can see on this slide was mentioned in topic 8.4. All right, now that we are convinced that in a weak acid, strong base titration, the pH will be greater than 7 at the equivalence point, let's go ahead and eliminate choices A and B, which say that the pH is equal to 7. So now we have to decide if the correct answer to question 3 is choice C or choice D. So there's one more thing I'd like to show you. This is one of the essential knowledge statements from topic 8.5, acid-base titrations, and it says the following. At the equivalence point for titrations of monoprotic acids or bases, the number of moles of titrant added is equal to the number of moles of analyte originally present. So the titrant, that is the chemical that is located in the burette, and the analyte, that is the chemical located in the flask directly beneath the burette. So because the number of moles of the titrant and the number of moles of the analyte are equal, In other words, because at the equivalence point, the moles of sodium hydroxide added to the flask are equal to the number of moles of the nitrous acid that were present in the flask at the start of the titration, that makes choice D incorrect. So the justification in choice D is that it says because the concentration of sodium hydroxide is greater than that of nitrous acid. But no, at the equivalence point, those two would have the same number of moles. So the correct answer is choice C. Again, the behavior of the conjugate base of nitrous acid, or the NO2 minus ion, acting like a weak base, that explains why the pH is greater than 7 when you have a weak acid titrated with a strong base. So again, the correct answer to question 3 is choice C. Now, as you make the transition from question 3 to question 4, you will notice some similarities and differences among these two questions. So both question 3 and question 4 involve an acid-base titration. But in question 3, we were not given a titration curve, and we didn't have to do any calculations involving moles or molarity. So question 3 was more of a conceptual question. Do you understand what are the major substances that are present in the flask at the equivalence point of the titration, and then how do those substances affect the pH at the equivalence point? But as you can see in the information for question 4, we are given a titration curve, and clearly there's going to be some calculations involving moles and molarity. So I'll go ahead and read question 4. It says, a 50.0 milliliter sample of a 0.20 molar monoprotic acid solution is titrated with a sodium hydroxide solution of unknown concentration. Now, the fact that we don't know the concentration of the sodium hydroxide, then that becomes the question. So based on the titration curve above, as well as the information that we're given about this acid, what is the molar concentration of the sodium hydroxide solution? And the word monoprotic, that means contains one proton or one H plus ion. So a monoprotic acid has the general formula HA. Doesn't matter whether it's strong or weak, and only one proton or one H plus ion is donated. That means that when it reacts with sodium hydroxide, there will be a 1-to-1 mole ratio between the monoprotic acid and the sodium hydroxide. Now right there, as you can see, I put a little dot on that titration curve. That would be the location of the equivalence point in this titration. And as I mentioned back in question 3, at the equivalence point of a titration, the number of moles of the titrant, in this case sodium hydroxide, are equal to the number of moles of the analyte, in this case the acid that is being titrated. Now let's calculate the number of moles of the acid, because we have both a volume and a molarity. So remember that if you're ever given both a volume and a molarity, you can calculate the number of moles. So it's volume times molarity equal moles. You first have to convert your milliliters into liters by dividing by 1,000, and then 0.20 molar of this monoprotic acid solution, that means that there are 0.20 moles of this acid for every 1 liter. If I do 50 divided by 1,000 and then times 0.20, I get the number of moles of the acid that was titrated in this experiment. So the number of moles of acid is 0.01. And based on that 1-to-1 ratio at the equivalence point between the acid and the base, that number is also the number of moles of the sodium hydroxide. Now we're one step away from calculating the molarity of the sodium hydroxide. So we know the moles. Where is in this information the volume of sodium hydroxide that was used to reach the equivalence point? Well, it's right there on the x-axis. You can see that sharp increase in pH. That's the location of the equivalence point. So we can see from the information on the x-axis that 25 milliliters of sodium hydroxide is required to reach the equivalence point in this titration. We've already calculated the number of moles of sodium hydroxide. It's 0.01. All we have to do now is moles divided by liters to get molarity. So 0.01 moles of sodium hydroxide divided by the volume in liters. So not 25, but 0.025 liters. If we do this math, 0.01 divided by 0.025, that will be the molarity. And when I do that math, I get that the concentration of sodium hydroxide is 0.40 moles per liter. So choice C is the correct answer to question 4. First, we calculated the number of moles of the acid. We recognized the 1-to-1 mole ratio between the acid and the base. And then we divided moles of sodium hydroxide by the volume required to reach the equivalence point, which we read from the titration curve. Now, as we move on to our next question and we see a new diagram, you'll notice this is another example of a titration curve. And at the top of this titration curve, it says that questions 5 and 6 refer to the following information. So let's go ahead and process the information from this acid-base titration. It says a 50.0 milliliter sample of a monoprotic acid, HA, so just like in question 4, we have an example of a monoprotic acid, of unknown molarity is titrated. The pH of the resulting solution is measured with a pH meter and graphed as a function of the volume of 0.100 molar sodium hydroxide added. The experimental data are shown in the graph above. So as you compare the information that we're looking at here with the previous question, recall that in the previous question, we knew the concentration of the monoprotic acid, but we didn't know the concentration of the sodium hydroxide. So now it's sort of reversed in this experiment. We know the concentration of the sodium hydroxide, but we don't know the concentration of the monoprotic acid. All right, let's move on to the specific details of question 5. In question 5, it says, a student carries out the same titration but uses an indicator instead of a pH meter. If the indicator changes color slightly past the equivalence point, what will the student obtain for the calculated concentration of the acid? Now, if you look at the 4 choices, you can see 2 different numbers for concentration. You can see either 0.0800 moles per liter for choices A and B, or you can see choice C and D with the number 0.125 moles per liter. So a good strategy is let's go ahead and calculate the concentration of this monoprotic acid. Much in a similar way to question 4, we can figure out the number of moles of the base, and then that would be equal to the number of moles of the acid at the equivalence point. So I'm going to consider the fact that we know the volume of the acid, but not the concentration. We know the concentration of the base, and we know that because the acid is monoprotic, there is a 1-to-1 ratio of moles between the acid and the base. So where is the volume of sodium hydroxide in this experiment? Well, you can read it on the x-axis by looking at that rapid change in pH at the equivalence point. So right there on the x-axis, it looks like it takes 40 milliliters of 0.100 molar sodium hydroxide required to reach the equivalence point in this experiment. Remember that if you know the volume and the molarity, you can calculate the number of moles. So let's do that. Let's calculate the number of moles of sodium hydroxide that are required to reach the equivalence point. So I'll start with volume, which would be 40 milliliters as read from the titration curve for the equivalence point. First, I will convert from milliliters into liters. So I'm going to divide by 1,000. And then I use the 0.100 molar sodium hydroxide as a conversion factor. So there are 0.100 moles of sodium hydroxide for every 1 liter. Now I pick up my calculator and do 40 divided by 1,000 times 0.1, and when I do that math, I get a number which is 4 times 10 to the negative 3. Now, that's not only the number of moles of sodium hydroxide that are required to reach the equivalence point, but based on that 1-to-1 ratio, the moles of sodium hydroxide are equal to the moles of the acid that were present in the flask at the start of the titration. So based on that 1-to-1 mole ratio in this experiment, I have 4 times 10 to the negative 3 moles of this monoprotic acid. So we know the moles, and we also know the volume. Remember that they had said there's a 50.0 milliliter sample of this monoprotic acid. So if we know the moles of the acid, and we also know the volume, then we can calculate the molarity. And the number that we're going to get is either 0.08 or 0.125. So here's my moles of acid, 4 times 10 to the negative 3 moles of acid, and I divide by not the number 50, but rather the number in liters. That would be 0.050. I'm dividing by 1,000 to go from milliliters to liters. And if I do this math, 4 times 10 to the negative 3 divided by 0.05, well, there it is. I get one of the numbers that was mentioned in these 4 choices. So 0.08 is the correct concentration of this monoprotic acid. Let's go ahead and eliminate choices C and D. But is the correct answer to question 5 slightly less than or slightly more than? Here is the specific details of this situation. Student carries out the titration but uses an indicator instead of a pH meter. So what does that mean? Well, if the indicator changes color slightly past the equivalence point, what I did was I drew that green arrow indicating that we're going to go a little bit past the equivalence point. So not 40 milliliters, maybe 42 or 44. I just picked a number. So I picked 44 milliliters, which would be a little bit past the equivalence point. Now I'm going to repeat those calculations that I had done earlier with the number 40. Volume, first from milliliters to liters, volume times molarity equals moles. Hopefully you can see that if the number of milliliters is slightly larger than 40, then the calculated value for the number of moles will be slightly larger than 4 times 10 to the negative 3. So I'm going to put a larger number of calculated moles of the sodium hydroxide into my calculation. That is also a larger number of calculated moles for the acid. So when I do that math, instead of getting 0.08, I get a number that is slightly larger than 0.08. So hopefully you can see that when you go a little bit past the equivalence point, your volume is too high, therefore your calculated number of moles of both sodium hydroxide and the monoprotic acid would be slightly too high. So correct answer to number 5 is choice B. Based on this error of going past the equivalence point, the calculated concentration of the acid would be slightly more than 0.08 moles per liter. Now, as we move on to question 6, it's the same titration curve, but now we have a different question to consider. Let's go ahead and take a look at question 6. Question 6 says the following. Based on the titration curve above, which of the following could be the identity of the weak acid? So the 4 answer choices represent not only 4 different chemical formulas, but we have 4 different Ka values. Now I'm going to show you one of the essential knowledge statements from topic 8.5, acid-base titrations, and it says the following. For titrations of weak acids or bases, it is useful to consider the point halfway to the equivalence point, that is, the half equivalence point. At this point, there are equal concentrations of each species in the conjugate acid-base pair. For example, for a weak acid, which is represented with the generic formula HA, the concentration of HA is equal to the concentration of A minus. A minus is the generic formula of the conjugate base of that weak acid. And because pH is equal to pKa when the conjugate acid and base have equal concentrations, then the pKa can be determined from the pH at the half equivalence point in a titration. So pH equals pKa at the half equivalence point. Now I'm also going to show you a graphic from my video for topics 8.4 and 8.5. And you can see I'm highlighting that at the half equivalence point in this weak acid strong base titration experiment, the pH equals the pKa at the half equivalence point. Let's go back and take a look at the graphic for questions 5 and 6. And we're going to focus our attention not on the equivalence point, but at the half equivalence point. So if the equivalence point is located at 40 milliliters on the x-axis, let's go to half of 40, which would be 20 milliliters. And what I care about is the pH at the half equivalence point. And so if you read the y-axis for the half equivalence point for this titration curve, you can see it is approximately 4. So the pH equals the pKa. In this case, that is approximately 4. Now, on the equation sheet, you know you can find all sorts of useful acid-base equations in this section of the equation sheet. So the pKa is equal to the negative log of the Ka. I'm going to take the negative log of each of these Ka values. Now, do I have to do this math? Well, I think it's a good idea, but if you roughly estimate that 10 to the minus 11, I have a pKa of approximately 11. It's 10.6. The next one, the Ka, it's 10 to the minus 8, and my pKa is 7.5, so approximately 8. Choice C is the correct answer to this question, but you can estimate without a calculator that 1.4 times 10 to the negative 4, the pKa is approximately equal to 4. I got a value of 3.85. So the correct answer to question 6 is choice C. At the half equivalence point, pH equals pKa. So for this experiment, that was a value of 4, and choice C is the one that has a pKa value that is approximately 4. Now, as we move on to our next question, we see another example of a titration curve, and the instructions above this diagram indicate that questions 7 and 8 refer to the following information. There's a very short description of this experiment. It says, a student performs an acid-base titration of a monoprotic acid, HX, and plots the experimental results in the graph above. Now, along this titration curve, we can see points that are labeled as A, B, C, and D. Those points will be relative to our answer to question 8. Let's go ahead and look at the details of question 7. In question 7, it says the following. Which of the following provides the correct information about this titration experiment? So we have to decide, is the acid a strong acid or a weak acid? And then what is the pH at the equivalence point of the titration? Is it equal to 7 or is it greater than 7? Hopefully, this question is going to be familiar to you from an earlier point in this video. So recall, question 3 talked about the fact that the pH was greater than 7 at the equivalence point for this weak acid strong base titration. Now here on this slide you can see a graphic, and I'm highlighting that in this titration curve, this was from my video for topics 8.4 and 8.5, it says that we have a solution of HCl. HCl, or hydrochloric acid, is on your list of 6 strong acids. And you'll notice that the pH at the equivalence point for a strong acid, strong base, is actually 7. The reason why it's 7 is because the anions, or the negative ions, that are produced in the ionization of a strong acid, they don't act like weak bases. They're actually neutral, and they have no effect on the pH of a solution at the equivalence point. That's why strong acid, strong base, pH is 7. Now, what about a weak acid? As you've learned, when you have a weak acid, strong base titration, the pH will be greater than 7. So this one's around a pH of 8. So again, these are slides from my video for topics 8.4 and 8.5. So the conclusion, strong acid, strong base, pH of 7 at the equivalence point, weak acid, strong base, pH greater than 7 at the equivalence point. This was also mentioned in topic 8.4, the idea that for a weak acid, strong base, the pH can be determined by the behavior of that conjugate base A-. And again, I'd mentioned in that graphic from my other video that you do have a pH greater than 7 when you have a weak acid, strong base titration. Now this should be pretty easy for us to go ahead and answer this particular question. Look at point D. That's the location of the equivalence point. It's around 9. So since the pH at the equivalence point is greater than 7, then this acid must be a weak acid. So is the correct answer choice A? No, that says a strong acid, so it's not A. Choice B also says a strong acid. So the correct answer is either C or D. It's a weak acid, but the pH is greater than 7, not equal to 7. So the correct answer to question 7 is choice D. A weak acid was titrated with a strong base, and the pH at the equivalence point is greater than 7. Again, this was very similar to question 3 earlier in this video, in this packet. Now, same diagram that we're going to use to answer question 8. Now, in question 8, we are given a particle diagram. It says, the particle diagram shown at right represents the relative amounts of major species in a sample of the solution in the flask at one point during the titration. Note that water molecules are omitted from this particle diagram. And the question asks, which of the points labeled on the titration curve, so A, B, C, or D, is most likely to represent the point in the titration where the reaction mixture would be represented by this particle diagram. Before I analyze the details of that particular particle diagram in question 8, these are slides from my video for topics 8.4 and 8.5. So what I'm doing is I'm moving along a titration curve and I'm changing the particle diagram as I go. So here at the very beginning of a weak acid strong base titration, I'm showing 6 molecules of the weak acid HA. Now I've moved a little further along the titration curve. I have 4 molecules of HA, and now I have 2 of the A- ions. Have we reached the half equivalence point? No, not yet. So there are more molecules of HA, there are fewer particles of A-. Well, at the half equivalence point, I have 3 particles of HA and 3 particles of A-, so there's an equal amount. And then when I go past the halfway point in the titration, now there are more particles of A- and there are fewer particles of HA. What happens at the equivalence point is that all of those particles of HA have been converted into particles of A-, the conjugate base. And if I kept going, there would simply be an excess amount of hydroxide ions if you move past the equivalence point. So again, once again, 6 particles of HA. Now I have 4 HA and 2 A-. I have 3 HA and 3 A-. Now I have 2 HA and 4 A-. And then all 6 are A-. Okay, let's go back to look at the diagram here. I'm going to count the HX particles. I have 2. So 2 molecules of HX. Now I'm going to count the X- particles. And I have 1, 2, 3, 4. So 4 particles of X-. So where on this titration curve would there be a solution in which there is a greater amount of X minus, the conjugate base, than molecules of the weak acid. So you're not going to be at the half equivalence point, you're going to be past the half equivalence point. So I have more particles of A minus than HA, or in this case, more particles of X minus as compared to HX. So where on that curve would there be a slightly past the half equivalence point? The best answer for question 8 is choice C. Point C should have more particles of X minus than HX. All right, well, that is the answer to question 8. Now let's take a look at question 9. Question 9 says the following. Data collected during the titration of a 20.0 milliliter sample of a 0.10 molar solution of a monoprotic acid with a solution of sodium hydroxide of unknown concentration are plotted in the graph above. So we know the concentration of the acid, we don't know the concentration of the base, the sodium hydroxide. The acid is monoprotic, so there's that 1-to-1 ratio that we've seen before. Now we come to the question, based on the data, which of the following are the approximate pKa of the acid and the molar concentration of the sodium hydroxide? Let's start with the pKa. I'm going to draw an arrow to show the location of the equivalence point. There's that rapid increase in pH, and that occurs on the x-axis at 20 milliliters. So that would be the location of the equivalence point. Well, half of 20 is 10, so the half equivalence point would be at 10 milliliters on the x-axis. Now, pH equals pKa at the half equivalence point, and if I look at the y-axis, that looks like the pH at the half equivalence point is just under 5. So the pH equals the pKa, which is slightly less than 5. Well, I've got two choices for pKa, 4.7 or 9.3. Okay, so it's definitely 4.7 and not 9.3. I'm going to eliminate choices C and D. Now, what about the calculated value for the concentration of the sodium hydroxide? You've already seen examples in this video of how we can calculate the number of moles of either the acid or the base. And if we know volume and molarity, we can calculate the number of moles. So I have the volume of the acid, 20 milliliters. I divided by 1,000 to convert that to liters. So that's 0.02 liters. I'm multiplying by the molarity as a conversion factor. So there's 0.10 mole of this monoprotic acid for every 1 liter. So 0.02 times 0.1, that gives me the number of moles of the monoprotic acid. So I got 2 times 10 to the negative 3 moles of this monoprotic acid. So based on that 1-to-1 ratio that we've seen between a monoprotic acid and a base like sodium hydroxide, that number, 2 times 10 to the negative 3, is not only the number of moles of the monoprotic acid, it's also the number of moles of the sodium hydroxide. But we need concentration, not moles. We need moles per liter. So where on the equivalence point would I find on the x-axis? I can see 20 milliliters. So the equivalence point tells me that 20 milliliters of sodium hydroxide is required to reach the equivalence point. I'm not going to divide by 20. I'm going to divide by that volume in liters. So I divide 2 times 10 to the negative third by 0.02 liters. Now you'll notice that I get an answer for the concentration of sodium hydroxide that is actually the same as the concentration of the monoprotic acid. So same volume, same concentration. 20 milliliters of acid, 0.10 molar. 20 milliliters of sodium hydroxide required to reach the equivalence point, same concentration, 0.10 molar. So the correct answer to question 9 is choice B. The pKa, as determined from the half equivalence point, is slightly less than 5, so about 4.7, and then the concentration of the sodium hydroxide matches the concentration of this monoprotic acid. Same volume, same concentration. All right, well, that's the answer to question 9. Now, let's take a look at question 10. Question 10 says the following. Acid dissociation constants, also known as Ka values, of two acids are listed in the table above. A 20 milliliter sample of a 0.10 molar solution of each acid is titrated to the equivalence point with 20 milliliters of 0.10 molar sodium hydroxide. And the question asks, which of the following is a true statement about the pH of the solutions at the equivalence point? And you can see in the 4 answer choices, is it a higher or a lower pH at the equivalence point? And we're referring to the acid that has the chemical formula CH3CO2H. Is it the stronger acid, or does it have the stronger conjugate base? What I'm going to show you on the next few slides are slides from my video for topics 8.4 and 8.5. It's a very similar question, so that might help you understand this particular situation in question 10. So on the left, I have one version of a weak acid. It's got the formula HC3H5O2. And then on the right, I have another weak acid, which is HOCl. At the half equivalence point, the pKa is around 5. And then for the other weak acid at the half equivalence point, the pKa is around 7.5. And so I was filling in the table with information about each of these acids from the titration curve. So we have the pH at the half equivalence point. Then I converted those pKa values into Ka values by doing 10 to the minus 4.89 and then 10 to the minus 7.52. Something you should know is that the larger the Ka value is, the stronger the acid is, or vice versa. The smaller the Ka value is, the weaker the acid is. So I can see from this data that HC3H5O2 is the stronger acid with a higher Ka value, and HOCl is the weaker acid with a lower Ka value. Now then I looked at the equivalence point. So for the substance that is the stronger acid in this question, the pH at the equivalence point is around 9. For the substance that is the weaker acid, the pH at the equivalence point is around 10. So there's this inverse relationship between the strength of the acid and the strength of the conjugate base. So we have a substance that behaves as the conjugate base, so C3H5O2-, and then we have another substance that behaves as a conjugate base, so OCl-. So based on the comparison of those Ka values and the initial pH, I've got the stronger acid and the weaker acid, but then looking at the pH at the equivalence point, it's weaker base and stronger base. Again, inverse relationship between the strength of the acid and the relative strength of the conjugate base. So really highlight this particular portion because this will help us answer this question. Stronger base, weaker acid. Weaker acid, stronger base, and then higher pH at the equivalence point. Again, there's an inverse relationship between Ka and Kb, as you can see in this equation on your equation sheet, that Ka times Kb equals Kw. So the smaller the Ka, the weaker the acid, but then the larger the Kb, the stronger its conjugate base. All right, now let's look at the Ka values for this particular set of acids in question 10. Well, the first Ka is much smaller than the second Ka. So therefore, CH3CO2H is the weaker acid. Now looking at all 4 of these choices, they're all referring to that formula, CH3CO2H. So I'm going to go ahead and write weaker acid, which is true, which means I can eliminate choice A, and I can eliminate choice C. So this substance, it is the weaker acid, but it also has the stronger conjugate base. So what about the pH at the equivalence point? Well, the substance that behaves as the stronger conjugate base will raise the pH of the solution to be a higher value at the equivalence point. So if you've got the stronger conjugate base, you are increasing the pH at the equivalence point. So correct answer to question 10 is choice B. CH3CO2H is the weaker acid, and it has the stronger conjugate base, and that's why it will have a higher pH at the equivalence point. All right, so number 10 is B. Now let's move on to question 11. In question 11, we are given a data table, and it says, experimental data for two different monoprotic acids are listed in the table below. So we are given the formula of the acid, we are given the concentration of the acid solution, we are given the volume of the acid solution, and then finally the pH of the acid solution. You might focus on that pH, and you notice that one of them has a pH of 1, so a lower pH, and the other has a pH of 4.27, so a higher pH. You also might realize that HClO4 is one of the 6 strong acids that you should memorize for the AP Chemistry exam. So the lower pH is in fact the stronger acid. In fact, the negative log of 0.1 is equal to 1, so that is definitely a strong acid. Now, is it important to know that one of these acids is strong and one of these acids is weak? Possibly. We'll keep going and I'll read the rest of this question. All right, question 11 says, two different titration experiments are performed, in which a 50 milliliter sample of each acid at a concentration of 0.10 molar is titrated with a 0.10 molar solution of sodium hydroxide. Now we come to the question, which of the following statements correctly compares the volume of sodium hydroxide required to reach the equivalence point in each titration? Now, I spent a little bit of time talking about how the fact that one of these acids is strong and the other is weak, but it's a very important misconception that a lot of AP Chemistry students have about this type of question. They would assume that a stronger acid will require more sodium hydroxide to reach the equivalence point. So, for some reason, students seem to think that a strong acid should require more sodium hydroxide to reach the equivalence point, and then they think that a weak acid should require less sodium hydroxide to reach the equivalence point. But that's not true. That's a misconception. So let me go ahead and be very clear. It's not about the relative strength of the acid. It's about the number of moles. Let me show you this essential knowledge statement from topic 8.5, acid-base titrations. It says, at the equivalence point for titrations of monoprotic acids or bases, the number of moles of titrant added is equal to the number of moles of analyte originally present. It's not about the relative strength of these acids, it's only about the number of moles. So again, this is the case for titrations of both strong acids and bases as well as weak acids and bases. So don't confuse the idea that one acid is strong and one acid is weak and think that that's going to be a difference. These two acids have the same number of moles, and that's the most important point to make this comparison. Same number of moles. Yes, one of them is a stronger acid and one of them is a weaker acid, but what I'm showing you here is they have the same volume, the same concentration, and therefore the same number of moles. So each of these acids contains the same number of moles of this monoprotic acid. It does not matter whether it's strong or weak. So the correct answer to question 11 is based on the fact that we have the same number of moles and not looking at the relative strength of the acid at all. The answer to question 11 is C. Each acid will require the same volume of sodium hydroxide to reach the equivalence point. All right, now let's take a look at question 12. Question 12 says the following. It says a solution containing HBr, which is hydrobromic acid. By the way, that is on your list of 6 strong acids that you should memorize for the AP Chemistry exam. So we have HBr, a strong acid, and we also have a weak acid, which has the formula HC2H3O2. That is known as acetic acid. So we have a strong acid, HBr, we have a weak acid, acetic acid, and that has a pH of 3. Then a change occurs. Enough sodium hydroxide is added to the solution to increase the pH to 11. So we're increasing the pH from 3 to 11. That indicates that an excess amount of sodium hydroxide was added to the solution. Now here comes the question. We've got 4 chemical formulas listed in this question. It says the amount of which of the following species increases as the sodium hydroxide is added. So let's analyze what we have before the sodium hydroxide is added. As I mentioned, HBr is on your list of 6 strong acids that you should know. So that is a strong acid which 100% ionizes in solution. And then we have acetic acid which partially ionizes. So we have a mixture of both molecules of acetic acid, and then we have some of those ions of what is called acetate, or the conjugate base of acetic acid. I'm going to draw a little particle diagram with some formulas inside. So we have H plus and Br minus from the strong acid, 100% ionized. But then we have a mixture of molecules of acetic acid with some ions of the conjugate base, acetate. Now all of this is present in the solution before the sodium hydroxide is added. Now, when I say sodium hydroxide, I'm really focusing on the hydroxide ion, not the sodium ion, but the hydroxide ion. Can the hydroxide ion react with a negative ion such as bromide? No. OH minus is not going to react with Br minus. Therefore, I don't consider the Br minus to be affected by the addition of sodium hydroxide. Can the hydroxide ion react with the acetate ion, or the conjugate base? I don't think that's a chemical reaction either between OH minus and C2H3O2 minus. So I'm already kind of looking at possibly the H plus being affected, but I think it's going to be affected in the wrong way. We're looking for a substance in which the concentration or the amount increases. Well, here comes OH minus reacting with H plus. Strong acid, strong base, you've seen that before. H plus and OH minus make water. We're looking for a substance whose amount or concentration would increase. H plus would actually decrease. So I can eliminate choice A because bromide is not really going to be affected by hydroxide. They're both negative ions and they don't really react to each other or with each other. H plus would actually decrease, not increase. Now I've narrowed down my choices to either C or D. You'll notice that acetic acid is classified as a weak acid. Here comes a strong base. Yes, definitely reacting with this weak acid. So here comes the strong base hydroxide. It's going to turn molecules of acetic acid into the ion acetate, or the conjugate base. So the correct answer to question 12 is choice C. When the sodium hydroxide is added to the solution, then the reaction represented by the equation above occurs, in which molecules of the weak acid will be transformed into particles of its conjugate base, C2H3O2 minus. So as a result, this causes the amount of that acetate ion to increase as sodium hydroxide is added. So the correct answer to question 12 is choice C. All right, now let's move on to the next question. This is question 13. This is also the last question in this packet. We are given a diagram with a titration curve, and then let's go ahead and take a look at the information in question 13. It says a 20.0 milliliter sample of a 0.10 molar solution of HF, or hydrofluoric acid, is titrated with 0.10 molar potassium hydroxide, KOH, and the data are shown in the graph above. Now here comes the question, which of the following graphs, so we have 4 graphs to analyze and consider, which of the following graphs shows the change in pH when a 20.0 milliliter sample of not hydrofluoric acid, but a different acid of 0.10 molar nitric acid is titrated with 0.10 molar potassium hydroxide. So the essence of this question is, if you switch from hydrofluoric acid, which is a weak acid, to nitric acid, which is a strong acid, how will the appearance of this titration curve be affected? So there are the 4 graphs that we have to analyze. Again, I mentioned that nitric acid is a strong acid that is on your list of 6 strong acids, but hydrofluoric acid is not on that list. So hydrofluoric acid is a weak acid. We have 20 milliliters of a 0.10 molar solution, and then nitric acid is a strong acid, but we also have 20 milliliters of a 0.10 molar solution. So same volume, same concentration, but one acid is weak and the other acid is strong. So I'm going to focus on the initial pH. Right now, the initial pH on this titration curve for hydrofluoric acid is a pH of 2. But if nitric acid is 100% ionized, then 0.10 molar is not only the concentration of nitric acid, it's also the concentration of H+, or the hydronium ion. So what's the initial pH of a 0.10 molar solution of this strong acid? Let's take the negative log of 0.1 and we can find out. So the negative log of 0.1, which is the concentration of the hydronium ion in this strong acid, is 1. So we are expecting that the initial pH for this titration curve is not going to be 2. It's going to be 1. So it starts off at a lower pH, which hopefully makes sense since that is the situation that we have. Now, as you can see, highlighted in yellow on the left side of the slide is the important point that I had made back in question 11 earlier in this video. It doesn't matter whether one acid is strong and the other acid is weak. It's not about the relative strength of the acids. It's about the number of moles of the acid. So each of these acids contains the same volume, same concentration of this monoprotic acid. Therefore, each acid will require the same volume of the titrant, potassium hydroxide, to reach the equivalence point. So right now the equivalence point occurs at 20 milliliters. I am looking for a graph among these 4 choices that starts off at a pH of 1, but the equivalence point would still be located at 20 milliliters. So let's go ahead and analyze these 4 graphs. So choice A, initial pH is 2, but I'm looking for an initial pH of 1, so I can eliminate choice A. Moving on to choice B. Again, initial pH of 2, I'm looking for an initial pH of 1, so I can eliminate choice B. Now, with choices C and D, the initial pH is 1 in choice C. Again, the initial pH is 1 for choice D, so those are potentially correct, but now look at the location of the equivalence point. In choice C, it's exactly where it should be, 20 milliliters, but in choice D, that's probably based on that misconception that I had mentioned earlier when I was talking about question 11. Some students might think that somehow a strong acid requires more of the base or the titrant to reach the equivalence point, but that's not true. It's only about the number of moles. It's not about the relative strength of the acid. So we can eliminate choice D. The equivalence point should be at 20 milliliters, not 40 milliliters. All right, so now hopefully you can see why the correct answer to question 13 is choice C. All right, well, this is the last question in this packet, so we have reached the end of the video. I hope that you found all of these answers and explanations helpful. Thanks for watching.